Okay, let's get started. So last time we did free body diagrams when the coordinate of choice was in the tangential and normal coordinates. So this time we're going to do the same thing, but now the coordinates of choice are going to be in cylindrical coordinates. Let me just review cylindrical coordinates before we get started with problems.
Are you going to post the notes online before lecture?
I did, right? Did you see it? Why don't I show it to you after in the break?
Okay.
So cylindrical coordinates are when you can represent the curve along which the particle moves in cylindrical coordinates. R equals f of theta, and the coordinate system is ur in the direction which the vector r is, and u theta is in the direction which the particle is moving. So in this case, the particle is moving upwards. So again, what you do is you draw the free body diagram. And you resolve the forces in the r direction and the theta direction. Once you do that, the equations of motion are simply summation of forces in the r direction, that is going to be mass times acceleration in the radial direction, which is mass times r double dot minus r theta dot square, and the net external force in the theta direction, so that's going to be m times r theta double dot plus 2r dot theta dot. Okay, and those forces are only the external forces. Now what might happen sometimes is you are given the forces in the normal and tangential direction, but the curve is given in r equals f theta coordinate frame. So this is what I'm talking about. So the curve is r equals f of theta, but the best way to find the external forces is in the tangential and normal direction, fn ft. Okay, so it's super easy to find ft and fn. It's hard to find ft fr f theta, and so in this case the question is which coordinate frame to use, right? Because the forces are in one frame and the curve is described in the cylindrical coordinates. So in this case, what you can do is there is a way in which you can resolve the forces from the Tn frame to the r theta frame by doing this. So this is going to be the vector in the r direction. Let's say this is the vector in the n direction. Note that this is in the direction opposite of Fn. This is just the way the forces are. And if this angle is, I don't know what this Greek symbol is called, psi. Okay. So if you know ur, un, then you can actually find psi. tan of psi is equal to r divided by dr d theta. So what you can do is you can find psi, right, from this formula. You can find psi because you know what r is as a function of theta. So you can find the right hand side in this formula, so you can find psi. So once you know psi, you know the angle made by ur with un. So you can resolve the forces ft and fn along ur and u theta. So you would have found ft and fr and f theta as a function of ft and fn. And so once you do that, it's just a matter of using the cylindrical coordinates to solve the problem. Is that clear? It'll be clear once I do a problem, if that's not clear. Any questions on this? Okay, let's solve problems. Okay, if the arm OA rotates with a constant clockwise angular velocity of theta dot equals 1.5 radians per second, find the force of arm OA which it exerts on the smooth 4-pound cylinder B, it's right here, when the angle theta is 45 degrees. Okay. Now the book does not say this, but in this case, assume G is 0. There's no gravity. The way you can do this without having gravity is this apparatus can be in the horizontal plane. So gravity will act like this. It won't act along the direction of motion. Okay, so let's just write what we are given. Theta dot is 1.5 radians per second. Mass of B is 4 lb. Given that theta is 45 degrees, theta double dot is, what's theta double dot? What's the acceleration? 0, because it's moving with constant speed. Okay, so why is this a problem of kinetics? It's because you're given forces. How are you given forces? It's only the forces due to acceleration. There are no external. Well, you're told to find. Sorry, you're told to find the force arm OA exerts, right? So if you're told to find forces, you have to use F equals ma. Okay, what coordinate frame do we use? We clearly use the cylindrical frame because the r is given as a function of theta. So free body diagram. So I'm going to draw a free body diagram of the mass so that I can use F equals ma. Okay, so the mass is acted on by it's on the arm OA. It's also sliding against the vertical, right? So when you remove the mass out of that wedge, it's going to be acted upon by how many forces? So it's held against this, it's held against that. If you remove those two things, how many forces will it be acted on by?
None.
No, it's acted by two forces because it's sitting against. When something is sitting against something else, and you remove the effect, you remove that support, it's going to be held on that place by a force. So it's going to be acted upon by a force through arm OA and also through the vertical sledge, or whatever you like to call it, the same. And the force is always going to be actually normal. Why? Because when you have a cylinder or something circular, the force always acts along the center. It cannot be in any other direction. So N, so that force is going to be in the direction actually normal to this. Okay. It also would have a force acting, this direction. This comes from the, I guess, the wedge, the thing which is standing vertically. So let's call that N1, let's call this N2, and this is again going to be normal, like this. Okay, are there any other external forces acting on the mass? There's no gravity. So that's about it. There's no other force. Okay, so we need, as I said, the best coordinate frame for this is the cylindrical coordinate frame. So UR, so it's acting, so it's said here, it's going clockwise. Okay, so this thing is turning like this, it's going upwards, which means that I would assume U theta to be in the direction in which the mass would move, which is upwards. Okay, so when I write the equations of motion, I would write them in the U theta frame, right? F of r is mass times the acceleration in the r direction. So I better find the forces in the r direction, which is this direction. You know that the forces N1 and N2 are not in the r direction. So you want to find the angle made by the forces with the r direction and the theta direction so that you can resolve the forces. So you're given that this is theta. So theta is the angle made by r with the horizontal. So this seems to be theta. Okay. So N1 cosine theta. Is there any contribution to do N2? So N2 is perpendicular to this, right? Which means that N2 acts along U theta. So there's going to be no influence of N2 in the radial direction. Clear? N2 is acting along theta, not along UR. So N1 cosine theta equals mass times R theta double dot minus R theta dot square. And F theta is the net force in the theta direction. So N2 acts along positive U theta. So N2, N1, you got to resolve that in this direction. So that's going to act in the negative direction of U theta. So N1 sine of theta equals mass times R theta double dot plus 2 R dot theta dot. Okay, so I think we are asked to find N1 and N2. Okay, only the force that OA exerts. So we are only asked to find N2. This is asked. So we're given theta. We're given the mass. We'll call that MB. Do we know what R is? R double dot and theta dot. We know what theta dot is, clearly. We know that's to be 1.5. It's written right here. We know this. We know what theta double dot is. Do we know what R is? No. Can we get R somehow?
45.
So you know this is 45. Okay. And so you know what theta is. But you also know that this is 4 feet. Can you use that to find R? So, yeah. So if you look closely, R cosine theta is equal to 4, and that length 4 is going to be a constant, right? As this arm OA moves up and down, right? R is always going to be the distance from O to the end of the vertical thing, this point here. So R is always going to r cosine theta will always be equal to 4. Yeah.
Is the mass 4 or would it be 4 divided by gravity?
The mass is 4 pound.
Wouldn't that be like the slug?
Oh no, you just have to use 4 there. No, sorry, you got to 4 divided by 32.2, right?
Yeah. There's no gravity.
Yes, right. So sorry. So it should be 4 lbs. You shouldn't use my bad. You shouldn't use 32.2. So think of 4 lb as kg, equivalent of kg. So if this was kg, what would you do? You just put 4 there. So it's exactly like that. And think of G 9.81 as same as 32.2. So if you see G and you want to do FPS, put pound British system, then you just put 32.2. Okay, so R is that. So we can find R is a function of theta, right? How did I get that? Where 1 over cosine theta is sec theta. And so if I can find R dot, I need R dot for this part. So R dot is, you know what the derivative of secant is? It's secant 10, right? Secant tan theta. And then you got to take the derivative of theta. And then R double dot is going to be this thing. It's going to be pretty nasty. It's 4 secant theta tan theta derivative of theta dot, which is theta double dot, plus, let's take the derivative of tan theta. So that's, what's the derivative of tan theta? It's secant square theta. So it's going to be secant cube theta times theta dot. Plus, I just need to take the derivative of secant theta. That's going to be secant times tan theta. So secant secant theta tan square theta theta dot. Okay, so I think I can find a numerical value for r because theta is 45. I can find a numerical value for r dot because I know what theta is. I know what theta dot is. I can also find a numerical value for r double dot because all these things are known. So actually comes out to be, so r comes out to be 5.657 feet. R dot comes out to be 8.485 feet per second, and R double dot is 38.18 feet per second square. And then if you use these values in this, then N1 is not asked, but I'll just write it down. It's 8.472, and N2 is 12. What's the unit of force in foot-pound? It's mass times gravity. So LB times gravity. Gravity is feet per second squared. So feet per second squared. Okay. Any questions?
Why are you using pound feet per second squared?
Isn't
it just pounds?
Because slug is the mass.
Okay, so I'm just looking at this. This is LB. And I'm looking at R double dot. So the units of N1 is the units of mass times acceleration. So units of mass is LB. Units of acceleration is feet per second squared.
But mass is slug. We already have
Is it given a slug?
no, but mass is slug.
You can convert this to slug.
Okay, I just always thought that force in that unit was just pound. Yeah.
I'm just looking at, okay, so what are units of N1? It's the units of mass times theta doesn't have units, so it's going to be units of mass times acceleration. The mass has units of pounds, and acceleration has units of gravity, is feet per second square. For the exam, I will definitely give you a problem in meters per second square. It won't be in 50. It's just annoying because most times you always have to deal with. Okay, so next problem. The collar has a mass of 2 kilograms. So this is the collar. It travels along the smooth horizontal rod defined by the equiangular spiral r equals E of theta, where theta is in radians. Determine the tangential force F and the normal force acting on the collar when the angle theta is 45 degrees. If the force F maintains a constant angular motion, theta dot equals 2 radians per second. So let's write what's given to us. Theta dot is equal to 2, theta equals 45 degrees, and theta double dot equals 0. Mass is 2 kgs. Okay, assume that gravity is 0, so this is again in the horizontal plane. What else? R equals f of theta. Okay, so is it the kinetics problem? Well, it is, because you're told to find the force, right? Yeah. Is it a problem? What kind of coordinate frame would you use? Clearly, you're given r equals f of theta, right? R equals E of theta. So you have to use cylindrical coordinates. So let's just draw the free body diagram. Okay, so this is a free body diagram. Again, you can draw multiple free body diagrams. You can draw it of the collar of the rod and so on. But since the thing of interest is the collar, I'm going to just draw a free body diagram of the collar. Okay, so F is an external force acting externally. Somebody is pulling this collar with the force F. That's given to you. What are the other external forces that are acting on the collar? What's that? Normal force, yeah. So there's going to be a normal force. And the reason why there's a normal force is when something is held against a groove, there is a force which is preventing it from moving laterally. And that force is the force N, which I've drawn here. If there was no such force, then it would simply not be held against the collar, right? Okay. Okay, so this is R. So this is going to be UR. UR U theta. Okay. Okay, so the question is then, this force is not acting in either the UR and U theta direction, right? So which direction is it acting? So it always acts in the normal and tangential direction to that particular collar. So so now this is the case I told you about. The forces are along the UT and UN direction, but the coordinate of choice is the R theta coordinate frame. So this is going to be U T because it's acting along F, and then UN is going to be in this direction.
Does that not act towards the center?
Oh, sorry, yeah, my bad. That's right. Okay, so what we've what I written down earlier was that you can find the angle made by R and N. This angle is psi, and you can find that psi by doing tan psi equals R divided by dr d theta. Okay. So since gravity doesn't act, those are the only forces. So let's write the equations of motion. So net force in the r direction is, so net force in this direction is going to be, psi. Since this is 90, this is also going to be psi. That's going to be 90 minus psi. So r direction, n acts, if you resolve n along r direction, it's going to point in the direction opposite to ur. So that's going to be n cosine psi. Right? F, on the other hand, is going to point along the direction of r when you resolve it. So F cosine of this angle, which is 90 minus psi, so that's sine of psi, and that's going to be, sorry, this is going to be negative, this is going to be positive. Equals mass times acceleration, so r double dot minus r theta dot square. Similarly, f of theta, the net forces in the theta direction, are n sine of psi, so that's going to point in this direction, so positive u theta, and then f will also point in the positive u theta direction, so both those have positive sign, equals mass times the acceleration in the radial direction, sorry, theta direction, that is r theta double dot plus 2 r dot theta dot. Okay, so we are asked to find f and n. Okay, so these are the unknowns. Do we know psi? Well, we know psi because we can find, let's try to find what psi is. Tan psi is r of the r, so e of theta, because r is equal to, I'm using this formula, divided by dr d theta. So derivative of e theta is simply e theta. So this is 1, so psi is 45 degrees. So psi is known. We know what r is, so we can find what r dot is going to be. It's going to be e theta theta dot. We can also find what r double dot is, simply e theta theta double dot plus e theta theta dot square. Okay, so r double dot is known, theta dot is given, theta double dot is given, so these things are all given to us. So eventually what will happen is you will get two equations with two unknowns, f and n, and you can solve for the unknowns. So turns out that when you do the math, f equals n equals 24.8 newtons. Two equations and two unknowns. Okay, is that clear? So again, to summarize, when we looked at the problem, we were asked to find the forces, so it was clearly a kinetics problem. Then we saw that we are given r as a function of e theta, which means that we need to use the cylindrical coordinates. However, the forces are in the tangential and normal coordinates, so we use this particular property where we can resolve the forces from the tangential coordinates to the cylindrical coordinates, and then we just set up the equations in cylindrical coordinates and solve for the forces. Okay, so you see that there is always the same thing in all the problems: FPD, equations of motion, and of course identification that the problem has to be solved in a particular coordinate frame.
Is it just a coincidence that theta equals psi?
Theta equals psi. Yeah, it's just a coincidence. It just depends on what r is.
Okay.
Okay, so last question. Okay, last question for today. So rod OA rotates counterclockwise at a constant angular rate of 4 radians per second. There's a double collar B. It's pin connected together such that one collar slides on the rotating rod OA. Okay, the other collar slides on the cylindrical rod. Okay, so this thing slides on OA, and the other collar, which is shown as C, slides along the circular rod, and you're given the equation of the rod, r equals 1.6 cosine of theta. If both collars have a mass of 0.5 kilograms, find the force which the circular rod exerts on one of the collars. So which this circular rod exerts on one of the collars, and the force OA exerts on the other collar, so it's going to be collar B at the instant when theta is 45 degrees. So motion is in the horizontal plane. So thankfully this time they've said that there's no gravity acting. So this thing is in the horizontal plane, so gravity cannot quite influence the motion in the horizontal plane. Okay, so first of all, is it a kinetics problem? It is, because you're asked to find forces. What kind of coordinate frame would you use? Clearly you're going to use cylindrical coordinate frame because you're told r is a function of theta, this thing. Okay, so then we just have to draw the free body diagram. Okay, now there are actually two collars, right? There's a collar B and there's a collar C. And you might be thinking, well, let me just extract one collar from the other and draw a free body diagram. But they've actually told you that both collars have a mass of 0.5 kilograms. This is a hint to you that you're better off drawing a free body diagram for the combined collars, not separating them, just because of this information. Okay, so we'll draw a free body diagram for both the collars. This is collar B, this is collar C. Okay, so collar B, this one slides on the rod OA. So when things slide along OA, assuming there's no friction, which it's told there's no friction, the only force acting on the collar is the force which is holding the collar in place. It's not allowing the collar to move in this direction. So the only force acting is going to be normal. So I'll call that force NP. Again, I just assumed it to be in this direction, but it can turn out to be in the direction exactly opposite to the way I've drawn it. Okay, the math will tell me if it's in the other direction.
But isn't that force in the opposite direction of motion?
This is the force acting on the, yeah, okay. So for collar C, which is this, it's sliding along the circular rod, right? So when it's sliding on the circular rod, the force acting along the motion is going to be zero unless there's friction, but there's no friction. So there's some force which is holding the collar in place on the circular loop. And that force is the normal force. So there's going to be a normal force acting on the collar, and I'm going to just assume it to be acting this way. So this is NC. And there's a special property of this force. It's always going to point towards the center of the circle. It's always true. the normal to a circle always passes through the center, and the force NC is along the center of the circle, so it will always pass through the center. Okay, I don't know if you know this property, but this angle is always twice theta. It's always 2 times this angle. It's always true. What's that?
Why is this next line?
It's always true. It's a property of the circle that the normal force, if you draw a normal from this is basically the arc of the circle, then this angle made by that ray, that line is always 2 times this. This is actually another point on the circle. It's always true. It's trigonometry. Okay, so are there any other forces? There's no gravity, so those are the only 2 forces. So given that, we have to just solve for the n. So all I need to do is write the equations of motion. Okay, so let's try to first draw the coordinate frame. That will make it easier to write the equations of motion. So UR is always acting along the R direction. U theta acts in the direction which the collar is moving. So you're told that it moves in the counterclockwise direction. So U theta is this way. Okay, I'm going to set up the equation and let you go because I'm running out of time. So the net force in the R direction, okay, is going to be NC cosine of 45 acting in the negative direction right? That's the only force acting because NB acts in along the U theta direction. So that is equal to mass times the acceleration. So R double dot minus R theta dot square. And then the net force in the theta direction is NB is acting along U theta. So I'll just write, so this should be NC. NB is acting along U theta, and NC, the component in the sine 45 component, acts in the direction opposite to U theta. So that's minus NC sine 45 degrees is equal to, maybe I should have written it as theta. Theta is mass times acceleration. So acceleration is R theta double dot plus 2 R dot theta dot. Okay, so given this, we know what theta is, we know what R is. It's 1.6 cosine theta. So we can find R dot. Please try to write this down. I'll complete this later on. So you can write R dot, you can write R double dot, so you can effectively find these things. So all you would have is 2 equations, 1 and 2, and 2 unknowns, NB and NC, and you can solve for NB and NC. It turns out that NB is equal to 0 and NC is equal to 25.6 newtons. So because NB is 0, don't be fooled into thinking that it's going to be 0 all the time. It might be 0 at this particular instant, but after moving a little bit, the force might turn out to be non-zero. So it's not always true. It's not always equal to 0. Okay, so I'll see you on Wednesday.
Normal for C also change?
Yeah, it'll also take some time.